So let's start the recording. Recording is on. Okay. Shall we start? Okay, so this is our second lecture, and first part of the lecture will be about presenting the problem of optimization in general, saying from a theoretical point of view. And the second part will be about starting with one-dimensional algorithms. And then, I don't know, I mean, if we can go to the, say, presenting at least an overview of the multidimensional algorithms. Otherwise, we will do it next week. Okay, so the main problem in most of the algorithms in applied mathematics is finding the minimum or the maximum, say, the minimizers or the maximizers for a function. Of course, this cannot be done using, say, the tools provided by, well, we use the tools provided from theory, but we cannot do any calculation, say, easily, unless some special cases. And so these special cases are somehow important because some of the functions that for which we are interested to find the minimizer or the maximizers have some special properties. So we can compute some of the quantities that are of interest. Okay, so let's state the general, say, form of this problem. So usually a problem, a minimization or maximization problem is called, is written in this way. So there is, well, let's say there is a function f of x for which we want to find the minimizer, and x subject to x in A, where A is usually a subset of Rn. And by the way, this is, well, in the problems, in most of the problems, n is large, extremely large. Could be, well, essentially could be, say, the number of, say, features in a machine learning model or something like that. So you have collected some data, and this is typically the number of coefficients you put in a linear model to find the minimizer for what you call, well, you see probably next semester, the cost function. So you want to minimize something, as I suggested at the beginning with the least squares method. So this is the general setting, and of course the other, say, the other problem, which is maximizer, to find the maximizers of f of x subject to x in A, is, say, the other side of the problem, but the two problems are related to one another because if you can find the minimizer, if you want to find the maximizer of a function, you can find the minimizer of negative that functions. The function is always a function whose codomain is R, so it's a real valued function. So taking the minimizer, finding the minimizer for f equals finding the maximizer for negative f and vice versa. So essentially, we will be dealing with the first problem, finding the minimizer of. Now I'm introducing you to the jargon. This is especially in what you see in, say, online in the books, in the few books that are many articles about these things. Well, this the problem written in this way is what is called a constrained optimization problem. That is, x is not free to take any value, but is required to be in a subset of the whole domain Rn. And usually the set A is called the constraint set or something like that. And this is the reason why this is usually called constrained optimization. Actually, this is not the true, let's say, the true distinction between constrained and unconstrained optimization. The real distinction about the two problems is about the nature of the points inside A, okay? So, well, we'll see this distinction in a moment when I give you say, the main theorems. But the idea is that essentially the problem is when you have, say, borders to the region, okay? So it's the same problem that you face when you are considering, say, one variable functions, okay? So say that you are given, say, parabola like this, and you want to find the minimizer. No, sorry, let's make it this way. Okay, and you want to find the minimizer for the function here. Well, of course, I mean, this is something obvious. The minimizer for this function over its domain is this point, is x0, okay? But if the x's are required to be, say, non-negative, for example, which is a very common requirement in most of the fields in applied mathematics, especially in economics, where most of the quantities must be non-negative numbers, well, then you actually can't see this part of the graph. You just see this part of the graph, and of course the minimizer is 0. And this is a problem because, of course, the usual method you use to find the minimizer, that is taking the derivative and finding where the derivative is 0, so finding the stationary points, is useless. And the reason for this is that the domain, well, actually, the domain where you are looking for the minimizer is a domain with a border, essentially. Let's say more formally from a topological point of view, not all the points in the domain are interior points, or, which is the same, the set A is not an open set, okay? So that is the big point, because if A is an open set, then problems like these cannot appear. That is the big distinction, working on open sets or working on sets that are not necessarily open. This is a problem that happens in many applications, linear programming and other things. Okay, so let's go with the definition of a maximizer. This is just as a reminder of course, it's the same definition that I gave you last year. So the definition, this is definition 2.1. And, well, we assume that we have a set A, which is an open, yes, we assume that A is open. And we assume that x0 is in A, and we have a function defined on A with real values. So we say that x0 is a minimizer, a local minimizer, if there is a number delta, positive number delta, such that f of x is greater than or equal f of x0, f of x is greater than or equal f of x0. This is a minimizer for all x's in A, such that the norm of x minus x0 is less than delta. And this is the definition of a local minimizer. A local minimizer is, say, an input for the function, a point in the space, such that the value at that point is less than or equal any other value in a given, well, in a neighborhood of that point x0, okay? So if you stay sufficiently close, that is a neighborhood. And this is the definition of a local minimizer. If you remove this condition, so if this inequality holds for every x in A, then you say that this is a global minimizer, okay? Which is the second part of the definition. I mean, just, I'm not repeating the same things. So local means it is true in a neighborhood, global means everywhere. Now, of course, the search is usually for global minimizers. Why? Because you want to find the best thing. And sometimes finding the second best or the third best is not that good. So essentially, let's say, even with functions of one variable, of course, this is a minimizer, a local minimizer. This is a global minimizer. And depending on the difference of the values between this and this, you might be interested in finding this number and not this one. Okay, so that is the idea. Of course, I'm talking about the x's. So this is x, I don't know, 1 and x2. Okay, so you're interested in finding x2. Now, the search for global minimizers and maximizers, global extreme values, is much more difficult because usually you don't have many ideas about how the function is. But there are many cases where finding the local minimizer means finding the global minimizer. Well, first of all, for example, every quadratic function, independently from the number of variables, has just one minimizer or maximizer, essentially because if you consider the derivative of that function, even all the partial derivatives, they are all linear functions. So when you, the condition that you already know, but we are going to restate it immediately. The first order condition say, if a point is a minimizer and is an interior point, then the gradient at that point is 0. Okay, so this is something that we have already seen last year. But that condition is, of course, is usually just necessary, but it becomes sufficient for global minimizer and maximizer for quadratic functions. And this is, for example, the case for a least squares case, because in the least squares, you are adding squares of errors. And so when you take the derivative, you get something which is essentially a linear system. And that's the reason why this case is important. Another case where the local minimizers are global minimizers is that with convex functions. For a convex function, there is a theorem that, not that difficult, there is a theorem that says, well, if a point is a local minimizer, then it must be also a global minimizer. There can't be, you can't be in this case if a function is convex. Well, you see it from this graph. This is kind of obvious. And the idea of the proof, just to quote it, say, briefly, the idea of the proof is just that, well, think of there is another minimizer. Then you can consider the segment joining the two minimizers, like this, well, this in this case. And of course, at some point, I mean, this is a local minimizer, but from the inequality that defines the convex sets, at some point you must go down one of the, say, the local minimizer, which is not global, okay? So you reach a contradiction. The contradiction is obvious if you think of a graph of a function in, say, a real valued function of a real variable. In the multidimensional case must be proved, but definitely is not that difficult, okay? So this is kind of an exercise, is just inequalities. And so you reach a contradiction. So that's the reason why sometimes just the information that the function is convex tells you that when you are finding the local minimizer, you are also finding the global minimizer, okay? And of course, the same is true for maximizers and concave functions. Okay. Sorry, I haven't told you, well, I give you the, to prepare these notes, I followed the notes that Professor Lucibello prepared last year, and two other books. One, well, I give you the details because in a post on Blackboard. Anyway, two books. And if you look at these two books, you'll see that the notations are quite different from one to the other. And essentially there is no, well, in mathematics this always happens, but in this case it's much more frequent than in the other branches of mathematics because the field is relatively new. And so there are many ideas, many people writing things. And so, and of course the perspective is somehow different because some people are interested in certain types of problems, and for those types of problems, some things are written in a special way. Okay, so another notation that sometimes we will use, but I used it sometimes in my notes as well. So when a point x star is a minimizer, a local minimizer of a function, so is the minimizer of f of x where x is in A. Sometimes we write x star equals arg min as x is in A of f of x, which looks like, say, more complex than the other thing, but so this is actually the argument of the function that makes f of x minimum at that point, okay? So this is just a matter of notation. I don't like using, say, too many symbols for the same thing, but anyway, sometimes I've used this, okay? And of course, again, the problem is, as I stated in an obvious example, the problem is with the set here. Okay, so we can move to the definitions we already know. So definition 2.2, just a matter of reminding the names. If A, with all the definitions above, so A is open, and F goes from A to R. And so we assume that x0 is a point in A, which means being A open means that x0 is an interior point. So the gradient of F, whenever the gradient of F at x0 is 0, well, I should say 0 transpose, we call this a stationary point. So we call x0 a stationary point. By the way, as you might have noticed, I didn't say anything about F being differentiable. For, well, I'll use explicit hypothesis in the following theorems, but essentially the people working in applied mathematics do not worry about all the things that mathematicians are worried about. That is, a function being differentiable, twice differentiable or not. They just say, well, we take a function and we suppose that the function is differentiable infinitely many times and things like that. So this is the completely different approach to mathematics. And I mean, you don't have to go too far. Even, well, just physicists, some of the physicists are more mathematicians than the mathematicians themselves. they just consider only, say, functions with all the derivatives, all the, say, differentiable infinity many times. Okay, so theorem 2.3, which we will now, this is a theorem we already know, because we have seen this theorem last year, but anyway, it's interesting to see the proof again, because it's related to some of the things that we see. Okay, so theorem 2.3 is called the first order necessary condition. So again, A is a subset of Rn, A is open, and F is at least C1 of, say, Rn. Well, it could be A actually, but let's say Rn. And we assume that F goes from A to Rn, to R, sorry. So the theorem says if Fx0 is a local minimizer, and sorry about that. Well, sorry about that. I didn't say this in the theorem. So I just said that x0 is a point in A, and that's the reason why the wording is slightly different. So, and x0 is a local minimizer, and it is an interior point. Then the gradient of F at x0 is 0 transpose, of course. Okay, so let's have a look at the proof. So we suppose that the gradient of F, this is a proof by contradiction, the gradient of F at x0 is not 0. So we take a direction, we take a vector p, which equals negative the gradient of F negative the gradient of F at x0. Should be transpose. I remind you that the gradient is a row vector. So that's the reason why when I set a vector, I mean, I need the transpose to get a column. So from this, we get that the gradient of F at x0 times p equals what? Equals negative the norm of the gradient of F at x0 squared. There's a typo in my notes. Well, by assumption, this is not 0. So the norm of F, the gradient of F is not 0. So this is negative. Strictly negative. So now we use the Taylor's theorem. And so we consider, now, if you consider this is negative, and this is actually what? This is the directional derivative of f along direction p. Okay, because the directional derivative is the gradient times the vector. So it says that the directional derivative is negative, and this is the thing that we are going, that makes the contradiction here. So what we can say now is that since the function here is continuous, because we assume that it's not just continuous, but also continuously differentiable. So it's continuous, and the derivative, all the partial derivatives are continuous. So what we can say now is that there exists a number t, capital T I used in my notes, yes, such that the gradient of f at x0 plus tp times p is negative for all t, lowercase t, in 0, capital T. What we know is local. We know that what we know is that the gradient at that point times the derivative at that point is negative. So we are now using continuity, which is essential for this, to extend this inequality to actually a neighborhood of a point. So it's not just there, it's everywhere. Of course, this is true locally, so we can't say for every t. So you move from x0 along the direction p, but at some point probably the inequality will become false. But if you stay sufficiently close, so there exists a t, capital T, could be small, but that doesn't matter, such that if you stay close to x0, then this is still true. And so by taking any value, I used another letter, guess, yes, tau. So for any tau in the interval 0 t, well, this is a lowercase t. Yes, no, it's an uppercase t. We have f of x0 plus tau p equals f of x0 plus tau, the gradient of f at x0 plus tp times p. Yeah. This looks like stating the same thing again with just another letter, but it's not technically, so I've used it a couple of times this. But so the idea is that, well, we are sufficiently close. You take a tau in this interval, and then what you can say is that if you look back at what I said last time, you remember that in the Taylor expansion, we can get rid of the little o term by actually changing this this term. Okay. By the way, this is the same trick we will be using in the last algorithm that I will present. Okay. So it's very important to remember this form of this thing. So we are actually saying, well, take any tau there, and of course you get equality here, and that equality is true for any t, which is in the interval 0 tau. So the t here is the theta that we have seen. Was it theta, I guess? The theta that we have seen last Thursday. Okay? Did I call it theta? Or well, usually I call it theta in the Taylor's Taylor expansion. No. How did I call it? Always T. It was T as well. Okay. Sorry about that. Last time, next time I will change the, the notation. So that is the idea, okay? And now, well, now this is obvious that this is strictly negative, and so we get a contradiction. Because we have shown that there is a whole neighborhood of along the direction P such that f of x0 is not a minimizer. Because we can go down. Values of f are decreasing if you follow direction P. Now you see why we need f to be an interior point. Sorry, x0, why we need x0 to be an interior point, because actually we don't know where the gradient is pointing. And so we must assume that P can be anything. So you don't know, x0 is supposed to be a minimizer. But this, say, this proof works, say, no matter P. So it must be that P could be here, or you don't know where it goes, where it points, okay? So you need the point to be an interior point, because otherwise this condition might not be true. Actually, I give you the reference on the book where I say, in the book that I took this proof from, which I'm giving you because, of course, it's quite interesting. It presents a number of algorithms in mathematics, in applied mathematics. And in that book is given also the algorithm for a non-interior point, okay? Well, for non-interior point, if you think of say you are here, and say this point, so this is, and this is a closed region, so the border is inside. So how can you say that this is a minimizer? Well, essentially, you follow the same reasoning here. So you look at all the directions, and you see whether along all the direction you're actually increasing, which means this is a minimizer. The only issue you have to consider is that not all directions are allowed. So you have to consider, say, directions like this, 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 and not this, okay? So not being at an interior point, say, adds more problem to the statement. But essentially, the proof is like this. By the way, this is something that is, again, another term that is used in applied mathematics. When you are in cases like these directions are called feasible directions. Feasible. and these are called unfeasible direction, okay? This is the feasible region, the things that you can do, the things that are allowed by being, so this is defined by the constraint. So the feasible directions are the one where you can go by staying in the domain, and the unfeasible directions are the ones that are not permitted. Okay, so that is the proof for the first theorem. Of course, this is just, you have a question? Yeah? Yeah? Okay, I go again, I review the proof, okay? So we started by saying, well, x0 is a local minimizer and it is an interior point. So we assume by contradiction that in addition to this, we assume that the gradient is not zero. So we choose as, say, a vector which is negative the gradient. Okay, so we are going in the direction that is not that of the gradient. And then we compute this. So we take the inner product of the gradient times p, which is the gradient times negative the gradient, which we get the negative, the norm of the gradient. And this is, by definition, negative because we assume that the gradient of f is not zero. Otherwise, this could be zero. And the reasoning will, that's the way we are working, because we are working by contradiction. Okay, so this is something that, and this is actually, let's say, essentially, this is the key to make to create the contradiction. Why? Because what you are saying is that there is a direction. If you see this as the directional derivative of f along p, you see that the directional derivative is negative. What remains below is just, say, the technical proof that this is actually a contradiction. But the idea is already here, okay? So to prove this, well, first of all, we rely on continuity of f and on the gradient of f, because we need the gradient of f to be continuous. So that's the reason why we require f to be C1. Because what we are doing is not taking the gradient of f at x0, which is supposed to be non-zero, but we are taking the gradient of f at some point which is close to zero. So we are moving from x0. And since we are moving from x0, we can't, in theory, we can't say anything about what happens there. But f is continuously differentiable, which means essentially that the gradient is continuous itself. And since the gradient is continuous and it is negative, non-zero, is non-zero, it must be non-zero in the same way. So this is a function of the gradient. If this is non-zero, it must be non-zero if you move slightly from the point because of the continuity, okay? And this makes this non-negative. It is negative at t equals 0. It is negative for some small t. We don't know how much small, but that's the thing. We know that there exists a capital T such that this is true. And then after that, we just rely on the Taylor expansion of this. So we take a variable tau and we say, well, what is the value if you move along that direction? Well, the value is the value at the point plus tau, which is the extension. Well, that tau is inside here, actually, but we moved it outside, times the gradient, times this. And by using this, I'm worried about the guys online when they can say by exploiting this, we get that this is negative. And so we prove that there are, if you move along the direction p, which is that opposite to the gradient, we are getting values that are less than the value at x0, and this contradicts the original hypothesis that x0 is a minimizer. Yes, please.
Sorry, if we know that the gradient times p is less than 0, don't we need to say that tau is greater than? Oh yeah, sorry, I don't see.
Okay. Well, this is just, I mean, mathematician stuff. I mean, this is not, the idea is over there. I mean, it's about, and it's not, well, you already know, this is something that, well, we have seen last time, that the gradient is the direction of maximal increase of the function. So that's the good reason for choosing negative p, negative the gradient as p is clear. Any other question? Tau p represents our h of the Taylor expansion. Exactly, Matteo. Exactly. Yes. 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 Tau p is the displacement. We are ending 10 to 1. Yeah? Yeah. just to get an idea. Okay. Okay. Of course, the second step in the search for the minimizers uses the second derivatives, and we will stop there, by the way. And even for second derivatives, well, of course, I mean, I didn't say the obvious that the condition there is a necessary condition, not a sufficient condition, of course. So the gradient being 0 doesn't tell you anything about by itself, but doesn't tell you anything about the point being a minimizer or a maximizer, okay? As I said, sometimes this tells you that exactly that, but because you have added some other, say, hypothesis to the model. But in general, this is not true. So we now go for the second order necessary condition, which is theorem 2.4. So again, A is a subset over N, and now F is from RA to R. And now we assume that A is C2 of A. Again, I used Rn. I don't know why, but anyway. And so we assume that F is twice continuously differentiable. That is not just the gradient, but also the Hessian matrix is continuous with respect to x1, xn, with respect to the input. So if x0 is an interior point, and a local minimizer, of F in A, then the gradient of F at x0 is 0, and this is something we already know. Mr. Transpose here, and D transpose times the Hessian matrix at x0 times D is non-negative, which is like saying that HF at x0 is positive semi-definite. So, well, the proof of this theorem is quite similar to the previous one. Of course, we already know this because of the previous theorem. So this comes for free. Well, it's stated in this case because, I mean, it's a more general version of, because of the two here. So we say that this is a local minimizer and say the function is twice continuously differentiable. The gradient is 0, and also the Hessian matrix at that point is a positive semi-definite matrix, which means take any direction and consider the quadratic form there, And so, and since this is the term of, if you remember, the Taylor expansion is still, well, f of x0 plus, which letter did I use? D here. Well, I used P as well. So why did I use P? Well, I used by contradiction. So I choose a vector P such that this is not. So the negation of this, so I started, well, let's give you a sketch of the proof, which is exactly the same as, quite similar to the previous one. So by contradiction, say there exists a direction P such that P transpose HF at x0, P is negative. So we want to get the contradiction. In the previous case, we chose the opposite, the gradient, and negative the gradient. And here we choose a direction for which this is not true. And the negation of greater than or equal to 0, of course, is negative, which means we assume that there is at least one direction where you can move, along which you can move, such that the value of the function, the value of this quadratic form decreases, is negative. And of course, this is the second degree term in the Taylor expansion, so you just do exactly what we did before. So you write it, the expansion, the first term in the expansion is 0, so you don't consider it, and so you are left with, so you write f of x0 plus p equals f of x0 plus the gradient of f at x0 times p plus 1/2 p transpose hf at x0 plus tp p. So again, the same trick we used before. And of course, this is 0. Because it comes from the previous theorem. And so you are left with this. And assuming that by contradiction, there is a direction where this is negative, well, you can say that if you stay sufficiently close, that direction is still negative, and you get, again, by continuity of the Hessian matrix, you get the conclusion. Well, the conclusion that contradicts the fact that x0 is a minimizer. Okay. If you look back at if you remember the proof of the, say, the first order condition in one variable case, to prove the first order condition in one variable case, you look at what happens to the right and to the left, and you assume that, and then by the existence of a limit, you conclude that the two derivatives must be equal. One of them is negative, the other one is positive, so they must be, sorry, one is non-negative, the other one is non-positive. And so the only way for them to be equal is that they are both equal to 0. And that is the key. And essentially, we are doing more or less the same thing here. Okay. Again, this is a sufficient condition and not necessary. Why? Well, because of the way, I mean, mathematics goes. I mean, actually, if you look at, it's like increasing or decreasing. The minimizers are, at a minimizer, what you can only guarantee is that the second derivative is non-negative, because negative would mean decreasing, but it could be 0 as well. Okay, this is even true in the one-dimensional case. But of course, we have sufficient condition. Well, essentially, the sufficient condition, which works in, say, the good way, is that when the quadratic form here is positive definite. Because when it is positive definite, then you can go the other way. Whenever you are sure that this term is positive, then of course, by guaranteeing that this is 0, So if the gradient is 0 and the Hessian is positive definite, then you can guarantee that the point is a minimizer. So you need a strong statement about the Hessian matrix, exactly in the same way as you needed a strong statement on the second derivative on, say, functions of a real variable, okay? That is the idea. And this is the sufficient condition that I will state now. Don't need this for now. And this is theorem 2.5. That says that, again, we have f from a subset over n to r. F is twice continuously differentiable. Here I said A, why? Don't know. And say X star is an interior point. I didn't get why we had to prove by contradiction. Wasn't it sufficient to do the Taylor expansion? Well, in a sense, yes. Yeah, I think so. Since it's positive semi-definite, with the Taylor expansion, we see that all neighboring points are greater than x0, so it's a local minimizer. Yes, I think so. What I'm thinking about is what happens in cases like this in the, yeah, but we are at an interior point, so I don't know. Yeah, I think so. Yeah, probably yes. I mean, for now, the answer is yes. I look into it, but I think that, yes, the answer is positive. Okay. So X star is an interior point, and so if first the gradient of f at X star is 0, and second, the Hessian at f at X star is positive definite. So then X star is a local minimizer. And again, the proof goes in the same way. So you use the, so if you stay sufficiently close, then the statement about the positive definiteness of H. So this makes the first degree term disappear. So you're left with the second degree, with the, say, D transpose. And if you stay sufficiently close in a neighborhood of X star, then this is, whatever the direction you choose, this gives a positive contribution to the function. And so X is a local minimizer. I wrote the proof in my notes, so you can look at it. But that is the the main idea behind this. Okay. And again, this is, of course, in the same way we work in the one-dimensional case. Yeah. Well, essentially because if you have, well, every positive definite is also semi-positive definite. But the idea is that it's like the second derivative. Of course, you can, this with matrices. With second derivatives, if the second derivative is 0, and this is essentially the problem in one variable, well, you don't know. So the idea is that think of, say, x to the fourth. I'm reasoning with just one variable, okay? So the first derivative is 4x cubed, and the second derivative is 12x squared, okay? Of course, 0 is a minimizer, and the derivative at 0 is 0, the second derivative at 0. But unfortunately, if you take x cubed, the first derivative is 3x squared, the second derivative is 6x, and again, the second derivative is 0 at 0, but it is not a minimizer. So this is actually the extension. The idea is that whenever a quadratic form is positive semi-definite, there are directions where you get 0, and there are directions possibly where you go up. But if there are no directions where you go up, you are lost. And actually, this formally is a positive semi-definite matrix. That's the issue. So that's the reason why this, well, this is exactly the same reason, if you go back to what I said last year, is exactly the same reason for which in some cases where the Hessian, the determinant of the Hessian is in the two-dimensional case is 0, then you don't know. The cases are, I mean, and it depends on say the algebra of the function. And so that is the main idea. Well, it's quite easy with one variable. It's slightly less easy in. Okay. Yes, 0, 0, 0, 0 is positive semi-definite, and also positive negative semi-definite. So, and actually tells you nothing about the function. Okay. So now we move for the first part, say, computational part of the, I don't know if I make a break now. We started one hour ago. And then we move on to the next part, which is more computational. Or would you like a break now or later? Is it okay now? No? Who votes for now? Who votes for later? Okay, now. Okay, so so is 20 past 11, so we'll be back around say 15, 20 minutes, okay? Okay. You guys online, can you hear me and see me? Well, see me, I think so, but yeah. Thank you. Guys, please. Shall we start back? Okay, so the second part, we are moving now to the computational part. So from now on, this part of this lecture and the next lecture, I will talk about, say, the algorithms. Of course, I'm not writing code. The code will be given to you by Professor Baldassi. I'm just giving you the, say, the mathematics and the ideas behind this. Now, let me just tell you that we are now moving from something that was done, say, essentially in the 19th, even maybe 18th century, to something that is a current field of research for many problems. It's not just that, of course, the mathematics behind it is well, it's a completely different type of mathematics in a sense. But also it has to do with the some of the say the way we do mathematics, that is with computers, and so some of the tricks and ideas are actually valuable, because it's not that they are valuable in themselves, but they are valuable because we are doing things in the way we are doing them, that is with the computer. So the first start is with one-dimensional optimization. So we are going back to the one-dimensional case to show a couple of examples here. And these examples are good because they provide a model, a one-dimensional model, so an easy-to-understand model that will be extended to the multidimensional case later on, okay? So the idea is, well, so for now we will focus on functions from R to R. And so the approach is, let's say we want to find the minimizer of a function. So the idea is we define a process, an algorithm that starts from a point X in the domain and finds another point and creates such, say, sort of a sequence, which is not a sequence because at some point it will converge possibly to the minimizer, and we expect this sequence, as I said, to approach the minimizer. At some point we will stop. We will see all these things in a moment. Why is one-dimensional search, because this is the way it is called, the search for the minimizer. Why is one-dimensional search important? Well, for two reasons. First, because yes, it is a model for many things, and sometimes is used as it is for solving problems, and also because it is used inside multidimensional problems sometimes, where the, say, the sub-problem that must be solved is actually a one-dimensional problem. So at some point in multidimensional problems, you go back to one-dimensional problems, essentially because you are just looking at one direction. And when you look in one direction, actually what you see is just one variable changing and the values of the function, okay? So our algorithms will start from an x0, and then we'll produce an x1, and which will produce in turn an x2, and so on. Okay, at some point we'll stop. We will see two algorithms. The first one is so-called Newton algorithms, so Newton method. And the second one is called the secant method. The big difference between the two methods is this one. Newton method uses f prime and the second derivative, while secant method uses just f prime. And well, for one variable function, using just using two pieces of information or one is not that big issue, because essentially computing the derivative or the second derivative is just one computation. But think of what this means for a multivariable function where the inputs are, say, n, with n large, and the output is a function of n variables. So computing an f prime means computing a gradient, which is n functions. And computing the second derivative means computing the Hessian, which means n squared function. And if n is large, this number might be the number of computations needed for computing not the second derivative, but the Hessian matrix could be huge. And so that's the reason why most of the methods in the multidimensional case, well, try to avoid this computation directly. Okay, so we start with Newton's method. It's quite surprising that we are quoting Newton, who made everything, actually, and in something that is applied now, I mean, more than 3 centuries later. So Newton method uses, as I said, f prime and the second derivative. And so the idea is that at every point and at every x1, x0, x1, x2, we can compute f of x, say, k. We can compute f prime at xk. We can compute the second derivative, f second, at xk. And the idea, well, the idea is quite obvious. Again, we use Taylor expansion. Did I tell you that Taylor was one of Newton's pupils? So actually, when you say Taylor expansion, Brooke Taylor was one of the, probably the most gifted of, say, Newton's pupils. So no surprise that Taylor is, well, actually, I read in a book that essentially Taylor's formula was used by Newton himself. So probably just say Taylor, say, took the time of writing things down, and because Newton was, well, this is very well known. Newton was not the kind of scientist that, say, keen to publish his findings, which is kind of surprising because. Okay, so what is the idea? Not a very smart idea from what we have seen so far, because it's actually using Taylor expansion, and instead of using f, using the second degree approximation given by the Taylor's formula. So what we do is we consider, where is it? Yeah, we consider a polynomial q of x, which is f of, sorry, yes, q of x is f of xk plus f prime at xk times x minus xk plus 1/2 the second derivative at xk times x minus xk squared. So this is Taylor's formula at xk, so at every step in the algorithm. And we suppose we have this, okay? And as we know, the Taylor expansion has the good property that equals, so q of x at xk is equals f of xk. Q of x, sorry, the derivative of q of x equals the derivative of at xk equals the derivative of f at xk, because if you plug in, if you compute the derivative, you get this, and this term disappears. And the second derivative of q at xk equals the second derivative of f at xk, which means the parabola here and the original function have not just the value, but also the value of the derivative and the value of the second derivative in common at xk. So this is, say, a good approximation. So what we are going to do now is well, we assume that this is a parabola. We want to find the minimizer. So what is the strategy? We consider the first order condition. We take the derivative and we make it equal to 0. So what is the derivative? What is q prime of x? Well, q prime of x is, just take the derivative, is f prime at xk plus f second at xk times x minus xk. And since we want to find the minimizer, we make this equal to 0, because this is a necessary condition. Okay? Okay, so we have f prime at xk plus second derivative at xk times x minus xk, oops, equals 0. And from this we get that x, if we want to solve this, we get that x minus xk equals negative f prime at xk over the second derivative at xk. And so x equals xk minus f prime at xk over the second derivative at xk. And this is Newton's method for finding the next step in the algorithm. Okay? So we are given xk, we compute f of xk, we compute, well, actually, we use f prime at xk and the second derivative at xk. We take the ratio of the two, and we get another number. And this number should be an approximation. It is an approximation, of course, because, well, what we did was, say, extremely rough. We just cut the Taylor expansion to the second degree, and then we discarded all the remaining terms. So, of course, this is not necessarily the right, say, the minimizer, apart from the special case where the function is a quadratic function, where it gives exactly the minimizer. So we get an approximation. So we call this approximation x sub k plus 1. So the algorithm is defined by sk plus 1 equals this. And so now this is in the form of something you can write in using code, okay? Okay, so let's see an example. Now, of course, my problem was with the examples here, because, I mean, the first reaction is that I will write some code, but the agreement with Professor Bardas is that you write the code, I'm just explaining the thing. So I'm using mathematics, which is not the right thing to do, but just to get the idea of what's going on. So say f of x equals 1/2 x squared minus sine of x. And so say that x0 is 0.5. So we start by 0.5 and say that we decide that our, say, the accuracy that we require is, well, looks like euros here, but call it epsilon, is 10 to the negative 5. Okay, so 0.00001. Of course, we need the first derivative and the second derivative. The first derivative is f prime of x is x minus cosine of x. And the second derivative is 1 plus sine of x. That is, we are relying on our knowledge of, say, mathematics, okay? So, what we do, well, what is x1? Well, going with the formulas, x1 is x0, that is 0.5, minus f prime at xk. Xk is now x0, so it's 0.5 minus cosine of 0.5 over the second derivative, which is 1 plus sine of 0.5. And if the computer is not mistaken, this is 0.7555. No, just 2 5s and a 2. Okay? And then you go on. At each step, you now feed this number in. This is x1, so you get x2, x3, and so on. And what is good is that in this case, we get x4, which equals 0.7390. And the good thing about x4 is that the absolute value of x4 minus x3 is less than 10 to the negative 5. So this is one way of stopping. Probably you have you already seen these things in, yeah. So this is one way, because of course, when you work with a computer, I mean, there are no zeros, there are no numbers. Do you know how computers are represented in memory? Say the bits, the IEEE, I don't know, the standard for representing numbers. Yeah. Do you? Yeah? Okay. So the idea is that, well, essentially the computer represents only a finite set of the rational numbers, okay? Which means that in the end, some numbers are not there and not just a finite set. You are working with a finite set. So all the numbers in an interval are mapped with just one number. And the interval is finite. And so what happens is that one way of stopping in an algorithm is this one. Another one is taking the ratio, and so relative error and things like that. Okay, so in this case, you stop. What is interesting here is that you stop here, and moreover, I also reported that the second derivative, well, the first derivative is actually 0, but the second derivative at x4 is 1.673, which is very positive. Very positive means that the function is locally, I mean, at least the approximation is locally convex, and so this is indeed a minimizer. Okay, so we have found the solution with the required approximation. That's the way that the method works. Of course, the first question is, well, you need to compute the derivatives and symbolic derivatives. Well, yes, that's true. And of course, you can do so only for functions for which you know exactly what the mathematical expression is, because otherwise you don't know. And sometimes, even if you know the mathematical expression, maybe the derivative is complex to compute for some reasons. So in those cases, what you do, well, you do a number of things, but one of them, say, especially in numerical calculus, this is a technique that is used in differential equations and solving problems where you have derivatives there, not just these ones. In those functions, you want what you do typically is approximate derivatives with, well, with what you learned in mathematics. That is the quotient between, say, the ratio of the difference in the function and the difference in the input. Okay, these are called finite differences. Finite means that it is in, say, against the limit that you take in mathematics. So they are not derivatives in a sense. They are approximation to the derivatives. They're like taking the limit and, say, instead of taking the limit, taking t sufficiently small or h sufficiently small, and then you get an approximation of the derivative. Another thing which is not that obvious, but it is obvious if you think of the method. Well, I said that this is a necessary condition. Yes, it is a necessary condition, but it's just necessary, which means that letting this be 0 is not a guarantee that what we find here is a minimizer. Why? Because, well, essentially it depends on the parabola being convex or concave. And this is the bad thing about Newton's method, because Newton's method works very well, but for functions that are with the second derivative that is strictly positive. And instead of many, of course, because you have to divide, and when you have to divide by the second derivative, well, first of all, if the second derivative is 0, bad news, because you run into problems into dividing a number by 0. And second, if the second derivative is even negative, you move in the wrong direction. This is very much better explained by figure 2.1, which I borrowed from one of the books that I'm telling you, and which shows that if you are at xk, and you have a concave function, if you look at figure 2.1, you see that instead of moving towards the minimizer, which is on the right, you are moving to the left, far from the minimizer. Because of what? Because the second derivative is negative, and essentially this ratio is negative, and with the minus sign in front of it is positive. Okay, so you get something. The derivative is negative, and you're moving the other way around. So this is an issue sometimes, but for some problems, as I said, it is not. And why? Again, for the reasons that I told you before, because when in many problems, namely the least squares and, say, some of the cost functions, in many problems, you know in advance that whatever complex the function is, but it is convex. And convex means, well, for most of the functions, means that if the functions are differentiable, means that the Hessian matrix is positive semi-definite. And sometimes you can even guarantee that it's positive definite. And so this is not a big issue for Newton's method. Well, of course, in applications, not in theory. Another way to look at Newton's method is to consider, I stay here, is to consider in this formula f prime as the function and not f. So if you, I stay here. If you set f prime at x equals g of x, well, the algorithm becomes xk plus 1 equals xk minus g of xk over g prime at xk. And now the method has changed the meaning, because the method is always the same, of course. It looks for the searches for the minimizers. But the minimizers, if you look at the derivative, are the points where the derivative is 0. So actually, this is not anymore a method for finding minimizers. It's a method for solving equations like g of x equals 0. Because actually, this is what we are going to do. And this is This is sometimes even taught in high school. It's called the tangents method for solving equation. Essentially, you start at the point, you take the tangent, and you go down. So you have a function like this. You start at the point, you go down, and then you take this, say, this is a, I don't know, a 0, like, no, not that thing, okay? So you take, this is the function, and so you start at the point here, you take the tangent, you cross the tangent with the x-axis, then you get the second point, so this is x0, this is x1, then you take the tangent, this is x2, and so on. And you move following the tangent. And if you do the math here, this is exactly the equation of the tangent line at the point g of x0, x0. Sorry, x0, g of x0. Okay? So that is another way to look at the same thing. Okay. And again, of course, this method fails if g prime is not 0. Well, this is obvious from the geometry, because whenever you have a point where the derivative is 0, from that point it's quite difficult to move. Okay, so now we go for the secant method, which is, again, as an interesting geometrical interpretation, but is, I give you first the, say, mathematical sort of interpretation. So again, we start with Newton's method, xk plus 1 equals xk minus f prime at xk over second derivative at xk. Now, say that you are unable to compute the second derivative. What are you going to do? You take the approximation of the second derivative. How can you compute the approximation of the second derivative? Well, you have already computed, because of the past, say, iterations in the algorithm, you have already computed f prime at the previous points, k minus 1, k, and so on. So what we are going to do is that, well, instead of the second derivative, you take the ratio. So you take f prime at xk minus f prime at xk minus 1 over xk minus xk minus 1. And you assume that this is an approximation to the second derivative at xk. So you see, the second derivative is the derivative of the first derivative, and we are just taking the variation in the first derivative over the variation in the input, and just taking the ratio. Of course, this is a rough measure, but as long as the difference between xk and xk plus 1 is sufficiently small, this is not so rough as it might seem. Okay? Sorry? Yes, of course. Yeah. Yeah, everything is like that. I mean, when I present the methods for multidimensional optimization, you see that all the gradients method are actually methods where you take the gradient and then you adjust the gradient, because what you are doing here, I mean, think of the Newton's method. What you are doing is, I'm moving from x along the direction of, well, it's not a direction because we are one-dimensional here, but I'm moving along, say, following the derivative, which is reasonable. But then the derivative is adjusted using the second derivative. So this adjustment in the one-dimensional case turns out to be just multiplication by a number, again, because everything collapses into number and you can't see anything. But you will see this in a much clearer setting in the multidimensional case. In the multidimensional case, this is not anymore a number. This is a matrix, so cannot appear here, or at least cannot appear in this way as something you divide by. So you need something different. We will explore that, but that is the idea, yes. So we get rid of a computation by using approximation. So we pay the price, of course, that is not necessarily the same thing, but the price we pay probably is actually less than the cost we incur if we go into the computation of all the derivatives. That is the idea. That is, well, in numerical analysis, there are many formulas for doing things, and it's no surprise that for formulas for these things, you are more worried about getting faster to the result instead of getting an accurate result. When I studied these things in universities, there were many, for example, there were many problems in differential equations that use actually technically how can you solve a differential equation? The differential equation is something like, I don't know, y plus y prime plus y second plus y third equals 0, for example, and y, say, y at 0 is 1, y prime at 0 is 2, second derivative at x0 is, I don't know, at 0 is 3, or something like that, okay? So you are setting a problem with a number of derivatives, and you're setting a starting point. So you are saying the function starts at 1 with slope 2 with second derivative 3, and then you go on. And you can find the third derivative by looking at this. Now, of course, to solve this, well, probably this can be solved mathematically, so by solving an equation. There are techniques, of course, but in general, you don't have techniques. So what you do is what? Well, you start with the derivative, and what are you going to do? Apply Newton's method. It's the same name, but the idea is that how can I go from a point to another point? Well, take the derivative here and move along the derivative. So instead of moving along the curve, you move along the derivative. Of course, you know that you are paying a price, but the price you pay is, say, probably is less than the cost. Now, the idea is that if you want to reduce the price you pay, what are you going to do? Well, instead of taking the first degree, so just the tangent, take the second degree approximation, take a parabola. And if you don't want to take the second degree, take the third degree, and so on. And of course, the longer the Taylor expansion you use is, the better the approximation. And of course, again, this is a trade-off between costing, computing values and time required for getting to the result. By the way, I don't know if you have used MATLAB, but MATLAB to solve differential equations uses a number of methods, and these methods are called ODE, stands for ordinary differential equations, and then they have two numbers. Like, I think that ODE 3.2 is 1, and the other one is ODE 4.3 or something. These two numbers are actually related to the length of the expansion. So if you want, well, they are called the Runge-Kutta methods because of the two mathematicians that worked at this. And these methods actually differ in the length of the expansion. Of course, this is more accurate. Yeah, it takes more time to compute. That is the idea. Okay, so, well, quite an interesting topic this is. Okay, so let's go back to the approximation here. So this is the secant method. Well, what is the secant method? Well, of course, you have to go through some algebra, and I outlined the algebra here. So essentially, what you do is that you rewrite. So instead of this, you use this. And so the formula becomes xk plus 1 equals xk minus f prime at xk times this monster. That is f prime at xk minus f prime at xk plus 1. Sorry, minus 1 over xk minus xk minus 1. Yes, yes, of course. Sorry about that. Well, let's fix it this way. Sort of. Okay. Let me point out another thing that does the second method use the approximation of the second derivative only if second derivative isn't available, or otherwise it just applies Taylor? Well, this method, I mean, the method works. Of course, whenever you know that you are making an approximation and the second derivative is somehow available, well, you can go for the second derivative. Of course, this is no, when there is no second derivative, well, it's quite difficult to compute the second derivative. You typically use this. But when you have the second derivative, it depends on how much it costs you to compute the second derivative. So there are, I mean, of course, there is no choice where you are unable to compute something, okay? In that case, you need approximations, okay? For some functions, you are unable to compute something because of... when you can compute, then, of course, you need an analysis to see which method is different. And usually, the analysis just try and see what you get out of, say, practical problems, okay? That is the answer. I hope I answered your question, Daniel. So let me point out, okay, let me point out another thing, which I think I wrote somewhere. Yes, at the very end. So let me point out that what we, actually, this is not that, I mean, you might think, well, I'm saving time in computing the second derivative, which might be, say, computationally expensive. But I'm also paying a price, another price, which is this one, the k-1 here. Because I need to compute the value at step k+1, I need the values at k, but also the values at k-1. Which means that I don't need more function evaluations, but I need more memory to store the numbers, because I need two steps. I can't use the variables at xk and then produce xk+1. I need also the values from the previous step, so I need to store them somewhere. So again, there is also a balance in the memory you are using, of course, sometimes. And have you done some, say, what kind of, did you see greedy algorithms with Professor Baldassi? What kind of algorithms did you see? I mean, sorry? Simulated, and did you see, say, for example, the computing of Fibonacci numbers? Like, no? So you were mentioning. Well, the idea in Fibonacci, well, you know, Fibonacci numbers are like 0, 1, 1, 2, 3, 5, 8, and so on. So every number is the sum of the previous two numbers, okay? And of course, if you think of computing using recurrence, you end up in a nightmare, because you are going back for every item, okay? So for example, say is 8, 13, and 21. So if you compute 21, you need to compute 13 and 8. And if you compute 13, you need to go down in the tree of recursion, in the recursion tree, and you have to compute down in the recursion tree for 8. Now, of course, the easy solution to this is that whenever you get something, so you get the Fibonacci, the third Fibonacci number is whatever it is, 2, or depending on where you start from. Instead of just forgetting, you store it somewhere. And then, of course, the computation becomes quite easy, because it's at every point you're not going back. Okay, so that is the, no, sorry, that is called dynamic programming, sorry. Yes. Yeah, I was confused about that. So, and that is the idea, the main idea of dynamic programming. So you, instead of computing everything, you just store something somewhere and then you use it again. And that is the idea. This idea has an interesting counterpart from, if you look at it, because we are working with second degree things. So second degree things are parabolas somewhere. And Newton's method uses function, derivative, and second derivative. Second method uses function and uses two values, 2 points, instead of 1 point and the value there. You uses 2 points and the derivative at the 2 points. So if you remember what you did in high school, one of the exercises, the typical exercise was find the parabola passing through these three, non-collinear points, okay? And that was one exercise, and that was just finding the point, so using only f. And the other one was find the parabola that has a vertex here, and the vertex, of course, is something more interesting, gives you not just the point, but also the special feature. You have formulas for the vertex. And that is the counterpart. So you are, instead of using points, you use derivatives there, which is the same approach that is used by in ordinary differential equation. Okay, so I've pointed out most of these things. The algebra for the second method is there. We now move to the multidimensional setting, okay? In the multidimensional setting, we do more or less the same thing. Now I'm presenting the thing, so I think I'm going, I think I'm going just to the end of page 16, more or less, just showing you the ideas here. So what is the idea? What are the ideas for multidimensional algorithms? Well, essentially, you work in the same way. You start at a point x, 0, and then you move to x1, x2, and so on. The problem is where to move. Okay, so you have x0, now they are vectors, x1, and so on, x2, and so on. And of course, what you typically do is find a next k plus 1 such that f of xk plus 1 is less than f of xk. Again, we are, considering only the search for a minimizer. Again, we need a starting point. By the way, the starting point is essential in some problems. There is a picture, a figure in my notes that shows that. It's figure 2.3, where it shows that if the starting point is not sufficiently close to the root, to the minimizer, then you might end up in problems. So that is the idea. So we want to create a sequence of points in Rn such that this sequence is approaching the minimizer. So the value taken at the next point is less than the value taken at the previous point, which is, we are decreasing. We are going in, the situation is getting better and not worse. Okay, so there are two main methods for approaching this problem in the multidimensional case. And we will use the first one. I will present a number of algorithms in the first one, which is the line search method. But also, I will present also the second one, which is interesting and sometimes it is used. So it's just for you to know. So the first one is line search. And the second one is the trust region. And in a sense, as I said, probably at the end of the yes, and in a sense, they are kind of complementary to one another. Okay? So what is line search? Well, line search says, well, you are at the point xk, and then you choose a direction where to move. So you choose a direction. I use the direction P, well, say PK, of course. But choosing a direction is not enough, because you need to produce a number, a vector that is another point. So you need to say also what is the displacement along that direction. So the next point will be xk plus alpha k pk. So you are moving along direction k by an amount alpha k. This amount is called, did I write this somewhere? No. Sometimes this is called the step size for obvious reasons. But in machine learning, this is also called the learning rate. I thought I told you somewhere this. No? Maybe later. I can't do a visual control F on my on my notes, okay? Well, what is the best way to choose the step size? Well, if you think of as, well, you're moving along a surface, okay? So think that say you are kind of, I don't know, for example, the interior of kind of a sphere, okay? Okay, so this is what you notice. And you are here somewhere, and you move along one of the direction. Of course, you are going downwards, which is a good thing. So this is actually what is called the descent direction. And this is probably well, we see that we will choose the direction so that it is a descent direction. That is the directional derivative along that direction is negative. So we are decreasing the value of the function. But the point is, you cannot go too far on the same direction, because think of anything, you are going down and then at some point you're back going up, which is something you don't want. So you need a method to choose the alpha k in the proper way. And the obvious method would be choose alpha such that alpha k, well, is the, well, say alpha k is the arg min of, say for the alpha positive of xk plus alpha pk. Okay? So essentially, you are minimizing the value of, I forgot an f here. You are minimizing the value of f. So you have transformed, by choosing a direction, you have transformed a multidimensional search into a one-dimensional search. And then what you do is just finding the minimum, so finding the minimizer. Since the direction is decided, you need to know just, say, how long to move in that direction. And this is the minimizer of this. Now, of course, this is, in general, an equation, and is a complex equation. And most of the methods do not solve this equation directly. Okay? So they use approximations to solving this equation, which is an equation in lambda. And a minimization in lambda, in alpha, and a minimization in alpha for which the value is the alpha k. I'm unfortunately, I don't have the remaining notes, but I think I solved that problem exactly later on in the gradient descent. So we will see again this problem in the general, in the special case of the gradient, the steepest descent or gradient descent, whatever it's called. And that is the idea of the problem. So in general, that would be the theory. And in general, you choose alpha in a way. Well, we will see that, but that is the idea of the line search. And the reason for which this is called line search is obvious, because, well, you are actually moving along a line. Yeah, please.
How do we choose the direction we take? Is it orthogonal to the level search?
Yeah, that is the most obvious direction is choosing the gradient descent, but actually we will see, yes, that's the topic that we will consider from, I think, next Thursday, yes. A brief mention about the other method. The other method goes in the other well, not direction, but say follows the other. Say exchanges the two problems, okay? So choosing the step size or the learning rate and choosing the direction are two, as I said, complementary problems. In the line search, you choose the direction and then the step size kind of is determined by the direction because you look for the minimizer, okay? In the trust region, you go the other way around. You choose your range, which is the trust region, and then in the trust region, you find the direction that gives you the least increase. Sorry, the maximum decrease of the function, okay? So essentially, the problem becomes that you want to find the minimizer of so first of all, let's be formal. Okay, so let's say you start from nx0, nxk plus p, and you want to find the minimum of, well, in theory, you should have f of x k plus p, but that would be computationally impossible. Why? Because p is undetermined. It's part of the unknown. Okay, so we want to minimize with respect to p. Okay, find the minimum direction given that the direction is not that large. Okay, so typically the condition is something like the norm of p is less than a given number delta. Okay, which means you stay in a neighborhood. Think of two-dimensional case. You stay in a disk, and you look which direction is the best for you to choose to find the minimizer. Okay, but then if you use f here, you run into big troubles because you have to evaluate f at some point you don't know. Okay, so the problem becomes impossible. So instead of using the function, you use what? A Taylor approximation, exactly. So, which is called, well, technically this is called the model. So m sub k is the model, so which means is an approximation to the function. And the idea is that the approximation of the function is something that must be close to. And usually m sub k at xk plus p equals f of xk plus the gradient of f at xk times p plus 1/2 p transpose bk p. Yeah. Hey. Just a moment. So you can't use f because otherwise you would be, all the components of p will be inside the f. Okay, it would be a nightmare to solve that problem. It would be a multi-dimensional optimization problem. in itself. So you use a model. The model is, well, a second-degree approximation. So you say, well, if I stay sufficiently close and the function is supposedly sufficiently smooth, continuously differentiable, twice continuously differentiable, well, actually, you typically require the gradient of f to exist. So at least you need continuously differentiable function. This is an assumption that, as I said, is frequently considered as reasonable in applications. And then you add a quadratic term, which is this one. But again, if you don't want to use second derivatives, you use BK. And BK is, we see some examples of, well, we don't see examples in the trust region because the trust region is not a method that I'm going to tell you about. I will give you the references anyway. But the idea is that if you don't want to use the Hessian matrix, the second derivatives, well, you can use an approximation of the second derivatives, like exactly as we did for the one-dimensional case for the second method, okay? There are many ways to approximate BK, and of course, the theory and, say, science is working, mathematicians and computer scientists are working to find good approximations depending on the problem and all these things, okay? So the idea is that, essentially, the idea is that BK is close to the Hessian matrix. So, again, you think of a model, you are confident that that model is sufficiently good to, say, it provides a good approximation to the function, okay? And then, well, you just run the code, okay? That is the idea. And that is the idea of the trust region. So you see that the two ideas are, in a sense, complementary to one another. And in my notes, before closing with this remark about the two complementary ideas, I wrote down the example with the Rosenbrock function. The reason for using the Rosenbrock function is that I also outlined some of the, I don't have it here because I don't know, for some reasons I don't have the last pages in my notes here, but the idea is that you have some, so the level curves are like this, okay? And the level curves actually for the trust region are important because the trust region, like you start from a point, then you see, you look for, you increase the delta. Typically what you do is you take a small delta and then there is no good reason, so you enlarge delta and then you move and then you choose this in this way. But you remember that the Rosenbrock function has a minimizer somewhere here, and the level curves here are here. So you can't see them if you are not in the right place. That's the problem. So that's the reason why I put this. Again, this is an example taken from another book, the other book that I'm referring to. And this is quite good to see that the trust region sometimes works, sometimes doesn't, because you think you don't want to move too far because, of course, otherwise, I mean, there might be, so you try to stay as close as possible, but if you stay as close as possible, you probably miss some of the, say, the minimizer, which is here. That is the problem with some functions. And so, of course, each method has its own advantages and drawbacks. And, well, as I said in the following, so next week, I will present all the methods in inline search, okay? One of them uses this, actually, so an approximation. Actually, most of the things use approximation to this, and they are all based on gradient. As you said, the direction is typically the gradient, apart from one case. So in general, you move along the gradient. Sometimes you just change your mind along the way. That is the idea. For example, there is one method that, well, Newton's method were exactly in the same way. We'll see. There is one method that actually, which is the last one, is called Nesterov momentum. momentum, for those of you who have done some physics, is say the fact that say if something is moving, tends to keep its moving state for a longer time before say friction stops it at some point. Okay, so instead of moving and finding exactly the minimizer, then it's like a ball going down. And if you think of a valley and you have a ball goes this way and then approaches the minimizer. But of course, if you think of the ball is not intelligent, so if it goes from say up down to the minimizer, then momentum pushes the ball up, and then it pushes down, and then friction does the job, okay, of say narrowing the valley and sending the ball to the minimizer. And that is the idea of momentum methods and of Nestor of momentum methods, which are kind of a second step in this. Okay, so I don't want to, of course, to start explaining this thing now, 10 minutes to the end. So this is the end of for today. And so the algorithms, the multidimensional algorithms will be presented next Thursday. Okay, see you. Oh, sorry, Matteo, I haven't seen your question. Both methods are repeated until we find the difference xk, which is very small. Yes, that is the idea. Yes, I will return on that, but that is the idea. The idea is this. Okay.